We're going to talk now about virtual memory. Let's look back a bit sort of historically. All right. If we want to do multiprogramming, what do we know? Well, we know for multiprogramming, the multi means we have greater than one process, right? We also know that a process has to be in memory to run. So let's look at the simplest possible way to do multiprogramming. We could do something like this. So we have our memory, all right, starting at 0. And let's say we have here the operating system at memory locations sort of 0 up to A. And then from A up to, let's say, A plus N, we have our process. So it runs, that's fine. And now the operating system decides, okay, it's time to run process 2. What the operating system could do is take process 1 and take its entire memory image and put it out to disk. And then take process 2 memory image that's already been saved and put that into disk. So it would do this context switch or switch of the memory and of course the registers too. And that would then allow us to run a different process. And what's the problem with that? Well, it's really slow. Writing to disk is extremely, extremely slow. It can take, thousands, tens of thousands equivalent instructions. So there's a huge overhead. But that does give us one approach. Now, so the isolation we have here, how are we isolated? So processes, so this is swapping, are isolated from each other. However, processes are not isolated from the operating system because there's nothing preventing process 1 from trying to access memory addresses between 0 and A. What we could now do for multiprogramming, rather than just having a single process in memory, is we could go ahead and have multiple processes in memory. Okay, and we could use equal, so fixed size equal partitions. In the previous case we talked about where there's a single process in memory, often what was happening, so if we look back historically, that was batch processing. We just have one application, one process in memory, and we let it run to completion. And then we put a new process in. The swapping idea that I talked about would work. As I said, though, the overhead is quite expensive. So let's look at this fixed size equal partitions idea. Again, from 0 to A will be where we locate the operating system. And then we'll go ahead and do some fixed size partitions of size n, and this is where we'll put the various processes. So process 1, process 2, and process 3. How well does this work? Well, so far we still have a problem in that we don't have isolation in address spaces between these processes. So if process 1 runs and accesses accidentally an address up here and writes to it, it's going to write inside process 3's memory. But will it work? So let's just assume everything is fully functioning in the sense that each process is both bug-free and not malicious. Well, yes, it will work. What are the downsides? Well, let's say process 1 doesn't really need to use all this space. Okay, so process 1 actually doesn't utilize this space. And process 3, or let's say process, and process 2 doesn't utilize a whole lot more space. Now, of course, you can't actually break it up sort of two-dimensionally like that, but we'll just assume there's a bunch at the top that it doesn't use. So this is an example of internal fragmentation, where we are wasting some space inside fixed blocks. Okay, so this is fragmented memory within allocated memory blocks. So that's one problem, in that if we have fixed size, equal partitions, well, we need to make that partition size large enough to hold the largest procedure or process, right? That means that any other process that's smaller is going to have wasted space for that. Is there a way we can get around this? Yes. So another approach we can use is fixed size unequal partitions. So for example, we've again got the operating system here. And then we've got, let's say, 3 processes. So process 1 here, process 2 here, and process 3 here. So the idea is that the partition size that a process runs in is big enough to run that process. So there's no internal fragmentation. However, we have a potential problem. Let's say that process 1 finishes. Okay, so it finishes. We've now got this free space. And now we go ahead and start running process 4. And process 4 is somewhat small. So it runs here. All right. And now let's say process 3 finishes. So we've got 2 areas of free memory here. Note that they're not contiguous though, and that's going to lead to a problem. And now let's say process 5 starts. And process 5 is this big. Still got 2 pieces of free memory. And now we want to run process 6. Well, process 6 is larger than this chunk of memory. It's larger than this chunk of memory, but is smaller than the combination of the 2. But we can't run. So process 6 can't run due to external fragmentation. That is, we've got fragmented memory. Not within an allocated block, right, but between allocated blocks. Fragmented because it's discontiguous, so it's got holes in it. So we've got a hole here and a hole here, and we can only use the larger of those holes, not the combination of those holes. Okay. So I remember this on the Mac OS back in the 90s, had this problem. And so what would happen is you'd run applications, and after a while there might be these holes, and you can't start a new one. And so the solution was, well, either restart the computer or just quit all your applications and then restart them again. So if you were running 2, 4, and 5 and you wanted to run 6 and couldn't, if you quit 2, 4, and 5 and then started 2, 4, and 5 up again, they would all be lined up from the beginning. They'd be contiguous to each other, and then the free space would be contiguous, and we'd have enough space to run process 6. So this is the fixed size unequal partitions. What it leads to is external fragmentation. And we're going to basically just be moving our way up and realizing over time how having hardware support can eliminate some of these problems. So this brings up a question about address binding. Okay, address binding is the question of when do we map instructions and data, the references to data and instructions to actual memory locations. So when do we map our instructions, instruction references, and data references to actual memory locations? As an example, right, if we are looking at some machine code, right, an instruction might say to, let's say, branch to, some address, 1, 2, 3, 4. So if this is part of my executable code, that sort of assumes my code is going to be loaded at a particular location in memory. And that's a problem here when we look at these different partitions, right? A process could be loaded starting at memory location A, or up here at B, or C, or so on. And so this branch OX1234 might work for process 4 if it's loaded here, but not necessarily for process 2 if it gets moved up, right? Or think of it rather as we have a process, it has this code in it, branch OX1234, so it assumes that that there's some particular code here at location 1234, and if location 1234 is in here, then if the process gets loaded into this partition, it's fine. But if it gets loaded anywhere else, that's a problem. So when does this binding happen? One place it can happen is at link time. Right, so at link time, the linker will take all these object files together, put them all together, figure out where this is going to be, where it intends for this process to be loaded in memory, and then makes everything all relative to that. So if it knows, if it figures it's going to be loaded at location A, let's say, then it can put the first piece of code starting at A. If this, and adjust all the branches appropriately, okay? And also adjust all data references as well. So address is used both for branch and call instructions, as well as address is used for, let's say, global variables and things like that. The stack's not an issue because the stack is going to always be using the relative to the stack pointer. And so if we had a stack at a different location, all it would have to do is just change the value of that stack pointer. So at ling time, we're basically using absolute addressing. We're using absolute addresses, and we assume that we know exactly where we're going to load it in memory. So that worked great if we were running one process that was always being loaded at a particular memory location. So good. If we know where we'll be loaded. Okay. But otherwise not good. Another possibility is at load time. So at load time, what can happen, right? Load time is when we actually take an executable and load it into memory. So that's similar in some ways to how the bootloader will load the kernel into memory. Okay, that's the loading the kernel into memory. In the same way, we'll load a process into memory. So we'll read it, it's executable, its ELF file. We'll read all of the different sections. We'll put them in different locations in memory. And so what could happen here is we relocate on the fly. That is, the executable is going to have information in it about every branch instruction, about every reference to any address. And then we can go ahead and update all those so that the code will be different if we get loaded at location A than it would be if we get loaded at location C, because every absolute address is going to be updated as we load into memory. A third possibility is position-independent code. Or position-independent, let's call it an executable. We get a nice acronym if we do that of pi. So position-independent executable would do something like this. It'd say, I'm not going to do a branch directly to a memory address. Instead, I'm going to do a relative branch. So we replace an absolute branch with a relative branch, where a relative branch says not an absolute address, but instead an address relative to my instruction pointer. So I might say, I want to go 100 before my instruction pointer, or 200 past my instruction pointer, something like that. And so the compiler and the linker together will combine to ensure that this position-independent code works. Now, there's still a problem if you deal with global variables. And so with global variables, we'd have to have some initial location of the globals. That is, we'd have to know the start of the globals. If we knew the start, every other global could be relative to the start. And so we would just have some register that contains, or some well-known location that contains where the globals start, and then refer to all the global variables with respect to that register. So we can say we're 0 from the register, we're 4 from the register, we're 110 from the register, and so on. That is, in fact, exactly how the Macintosh worked. All the code was position-independent code, and all the references to global variables were with respect to what was called an A5 register. They were called A5 globals. Another alternative is to do this at runtime. Okay. In order to do it at execution time, at runtime, we're going to need the help of a little bit of hardware. Okay, and that hardware is going to be called a relocation register. So what's going to happen is the code is going to use logical addresses. and these are going to get converted to physical addresses. So what will happen? Well, our logical address, so let's look at process 2, let's say. So it is going to assume it's going from 0 to n. All right, that's its logical addresses. So it's going to be compiled and linked such that as soon as it gets loaded in this area of memory. And then what will happen is we'll have this relocation register. And the relocation register is going to have a value of b, this b here. Okay, that is the base of where our process actually gets loaded into memory. And then what happens is any reference to a logical address, right, so this is logical, is going to get added to the relocation register. So we take a logical register, for instance, let's say we do, address 32. So address 32 gets taken in here, gets added to B, and this gives us out a value starting from B. So logical coming in, physical coming out. What that means is if we're running process 2, we want the relocation register to be B. However, if we now go ahead and context switch into process 5, we just need to adjust the relocation register from B to C. This provides us also some isolation. Okay? None of these processes can access the operating system. Why? Because their lowest address is 0. And so it can't go below the relocation register. Now we'll just have to say, let's assume that the plus doesn't overflow. So we'll have to make sure that if we went past the end of the address space, that it doesn't overflow back to the beginning. Okay, but that's easy enough to ensure in the hardware. So none of the processes can access physical memory that is lower than that of the relocation register. Now it is certainly true we still have a problem with isolation in that, for instance, process 2 can go ahead and read and write process 5's memory. Process 4 can read and write any process's memory because it happens to be loaded first. We will go ahead and make some adjustments to remove that problem. And just to make clear, when we talk about these logical addresses, right, so we might have some code that says branch to 32. All right. So the processor is seeing logical addresses. When the processor sees this branch 32, it's going to go ahead and update the instruction pointer to point to 32, and then fetch whatever is at memory location 32. So it's going to do a fetch of 32, right? Because that's what the processor does. It does a fetch, decode, execute, and the execution of this 32 is to update the instruction pointer, and then the next fetch goes ahead and fetches whatever's that instruction pointer. So it's going to fetch from address 32. That's what the processor is thinking, address 32. However, before we go to the memory bus, the relocation register, which is part of the MMU, is going to say, I am going to go ahead and convert that logical address to a physical address by adding B to it. So when it goes out to the memory bus, it's not 32 anymore, it's B plus 32. So it's going to return whatever is at location 32 within this process 2's memory location. And so then that value is going to be returned to the CPU. And so the CPU is going to get whatever instruction was at location B plus 32 in main memory, in physical memory. But it doesn't know that. The CPU, thinks that it was location 32 that it was getting that from. Okay. So this relocation register is basically affecting every address before it goes to the memory bus.